This, children, is a true story. During voting at by-election, an exit poll, 1,700 voters indicated 50% of people had voted for the Labour Party. When the votes counted, found that, in fact, 57% of the support. 850 of the fixed number of people that we have said they voted for Labour, but 57% of the 1,700 is 969, a much higher number. What went wrong? Is it possible to see how lucky, so on and so forth. Now, the key thing to notice here is the 1,700. It's a fixed number of people. If we assume that everyone votes independently of each other, then actually what we've got is a binomial distribution. X is binomially distributed with n and p, and n in this case is 1,700. P is 0.57. Then, well, that is our binomial distribution. And so, if we wanted to find out this on a binomial distribution, then we'd be asking the question of, well, actually, I want to work out what is the chance that I get 850 people voting for Labour. Now, don't forget, when you do that, you'll get an individual number for 1, 0, 1, 2, 3, 4, 5, all the way up to 850, and actually you're wanting every single one of those to be added up. Now, with a binomial distribution, that's not reasonable or feasible to do in any time. If you've got a computer, fine, but what we do here, as we saw in the last video, is we approximate it, and we say that X is actually normally distributed with a mean of n times p and a variance of n times p times q. So in this case, X will be modelled by a normal distribution with 1,700 times 0.57, so 969 mean, I can't even think at the moment, and a standard deviation of, or a variance rather, of 1,700 times 0.57 times 0.53. So NPQ is 1,700 times 0.53 times 0.47. So that will come out to be, and then we'll square root it. So I get basically 20.4 squared for the variance. Now this works for n being large, and p isn't too close to 0 or too close to 1, making it very small, in either direction rather, I suppose. So actually it'll be quite a good model. And now that we've got that, where am I? Thank goodness for pause, eh? Now that I've got that, I can actually look at it on a normal distribution. So I've got 969. I've got a standard deviation of 20.4. Notice I've put 20.4 squared. In theory, I should really put a square root of a value, and that would be much more accurate. But I'm quite happy to not do it again on my calculator. So I then want to find out 850. Now, if I remember correctly, we're dealing with people here. And in our last section, we looked at continuity correction. And so 850, actually, I want to include all 850, so I can't put 850 in there. I have to put 850.5. If, for example, I wanted 850 or above, then I'd put 849.5. So I need to find out this area here. Now, finding out that area means I need to go into standardized scores. So my standardized score is 850.5 minus 969 divided by the standard deviation of 20.4, and so that comes out to be minus 5.8. So I'm going to then have to work out minus 5.8, which I'm not really sure we're going to be able to do. Now if that's minus 5.8, that's 0, that's 5.8. So to work out this area, I'm going to do 1 minus phi of 5.8, and 5.8, if we look in our formula book, for our z value, we shouldn't really have a z value that high, and there we go. Now, we only go up to 3.4, and in fact, the probability of this comes out to be something like I think it's 1 over 100,000. So effectively, it really is quite unlikely that this was just a random sample. Yeah, it's much more likely that there's some other explanation. So, voting by election next poll of 1,700 votes indicate that 50% of people had voted for the Labour Party candidate when the votes counted, in fact, at 57%. So, I don't know, they might have been voting outside a Tory section. There's just some other explanation. Chance of it actually being correct, well, we can't have those values. And like I said, if you look in the formula book, well, 3.4, 4 standard deviations, 5 standard deviations, it's just going to be minute.